All right. So fission is where we take a heavier atom and we break it into two smaller parts. Fusion is we take two small atoms and fuse them together into making a larger one. Fission is more what we are exposed to here on Earth. It's where we're going to take heavier elements. They're going to decompose into more stable elements. You also sometimes produce neutrons. We call that fission because it's breaking apart. The breaking is rather random with the formation of a large number of different products. And fission usually does not occur naturally, but is induced by bombardment with neutrons. So they're going to take a heavy element and they're going to hit it with neutrons, and that causes it to break apart. And that's how like nuclear bombs are created. Okay. That's also how, in a much more controlled fashion, they make nuclear energy. So they'll take these bigger elements and they hit it with some neutrons and it makes it break apart. And when it breaks apart, it gives off energy. And then they can use that energy to do things like heat water, which then turns turbines and creates electrical energy in a generator. So for example, if we had uranium-235, we could hit that with a neutron. It's going to split apart here, and it's going to give off some energy in the process. And we talked about these nuclear equations where we go through, we hit it with a neutron. It's going to create this. Its mass would have gone up because it had more energy or more neutrons in there. The number down here stays the same because a neutron doesn't change that bottom number. Only a proton does. And then that uranium is going to be so unstable that it's going to break apart into two other things. And then this gives off 3 neutrons. Those 3 neutrons then can go in and hit more uranium. And then that would produce 9 neutrons. And then those 9 would produce 27. And those 27 would produce, I think it's 81. But you can see that that just keeps going on and on and on. That's called a chain reaction, where they just continue to produce more and more of these. And then that's giving off more and more energy. So in a nuclear power plant, they have to control that. And we'll talk about how they do that in a few minutes. Nuclear fission then is going to produce an incredible amount of energy. So for example, 1 kilogram of uranium will produce 2.5 million times more energy than a kilogram of coal. A kilogram is 2.2 pounds. So 2.2 pounds of this stuff will produce 2.5 million more times more energy than 2.2 pounds of coal. That's a crazy amount. Right? When this fusion produces 2 medium-sized nuclei, they're also going to produce these 3 neutrons. Those then will produce more, and they continue on. We call that a chain reaction. Do you guys have anything to fill out for these? Am I going too fast?
We only had the chain reaction.
Okay. So here's what we were talking about with that. We hit this with 1 neutron. That neutron creates these guys and 3 more neutrons. That's going to go and hit some more uranium. It'll produce these and 9 neutrons, and it just keeps going and going and going, and it's like this continuous process. So nuclear fission becomes self-sustaining. So they hit it with 1 and it creates more neutrons. The amount of fissionable material that can support a chain reaction is called the critical mass. An amount of fissionable material that can't sustain a chain reaction is called subcritical mass. So, for example, if we didn't have enough of these in there to be able for these neutrons to find something to hit, that would be called subcritical. So they have to have just enough material in there for them to be able to hit that uranium. If there is an increasing amount of fission, then that's called a supercritical mass. The critical mass also depends on the type of material, how pure it is, what the temperature is, the shape of that sample, and then how the neutron reactions are controlled. So, for example, if we have a subcritical mass, there might not be enough material for those neutrons to find something to hit, as opposed to here, where there would be enough material for it to find things. Atomic bomb then is going to contain several pounds of either uranium or plutonium, a source of neutrons, and an explosive device to get all of this stuff shoved together well enough to be able to find the neutrons to find something to hit. When that material is in small pieces, the proportion of the neutrons that can escape through the relatively large surface is great, and we don't get a chain reaction. But when it's small enough and they're brought together really quickly, then we have a mass larger than the critical mass, and they're able to sustain that chain reaction, and they create an explosion. So here is an example of what these bombs look like. This was one of the ones that they used over Japan back in World War II. This is one of the designs where they had a conventional explosive and it rammed into this uranium. And then they've got another one where, and they had two different designs because they were hoping that one of them worked, and both of them actually worked. The one they hit Japan with, and Japan didn't surrender. And then they went back like 3 days later and they hit Japan again with another one. And then Japan's like, okay, uncle, I give. Luckily, they gave because that was the last bomb we had, but they didn't know that. Yeah.
Sorry, can I get you to go back? All right, thank you.
So one of these was called Fat Man. I'm guessing it was this one. And then the other one was called Little Boy. And those were the ones that they used to bomb Japan with. And then they've created other ones since then, but nothing, as far as I know, has been used in any kind of military campaigns. Now, they've tested a bunch, you know, and they've got a bunch around, but they haven't actually used them since then in wartime, thankfully. Chain reactions, then, of fissionable materials can be controlled and sustained without an explosion in a nuclear reactor. And there's nuclear reactors. We have a couple here in Wisconsin. There's several down in Illinois. And these reactors produce power through this fission process. We're going to bombard uranium and plutonium, and we have to have at least these 5 components. We have to have a nuclear fuel that has enough fissionable material in it. They have to have a moderator which will slow down or stop those chain reactions. They have to have a reactor coolant so the thing doesn't get too hot, the control rods, and then they have to have shielding and containment. You don't want that nuclear radiation getting out into the environment. When we watch the video tomorrow and the next day, they'll actually talk about Chernobyl, and that was in Ukraine, or what was Russia back then. And they're also going to talk about Fukushima, which is in Japan, and they had a nuclear accident there too. And they'll go into kind of the history behind that, what went wrong, why these things happened. Now, I'm not sure about the ones in Japan, but the nuclear power plants in Russia are built very differently than the ones that we have here in the US. The ones that we have here in the US have a lot more safeguards built into them than the ones in Russia do. So as far as like people being worried about the nuclear stuff, I mean, there's always stuff to worry about, but that's really not one that, you need to be terribly concerned about in this country, especially as far as we live away from nuclear power plants here in Janesville. It's not a big deal. The reactor works by separating this fissionable material. They're going to control how many neutrons are created. That's what the flux means. And how many are absorbed. And they're able to shut down those reactions by using those control rods. In the nuclear reactor that's used for electricity, your energy that's released is trapped as thermal heat, and that's used to boil the water and produce steam. And this is exactly what our power plants do here that are coal-fired. They produce thermal energy, they boil water, that produces steam. The steam then runs the generators, which create our electricity. They also have like hydroelectric plants. The hydroelectric plants do a similar thing where they're going to end up having the water flow will turn the turbines and produce that steam. Instead of steam turning the turbines, the water does. This is what a typical nuclear power plant would look like. These are your reactors here. And these are made of concrete and steel and very, very thick because A, they want to be able to, if there was an explosion in here, they would want to contain it. And B, they want to make sure that it's shielded enough that none of the radioactive material, the gamma rays and that sort of thing can get out. They also make these as a domed shape because a dome shape is much more structurally sound than a square shaped building. Okay, that's why when you see like tanker trucks that have gas in them, that's why they're always dome shaped on the ends, because that structure is a much stronger structure. The nuclear fuel then has a fissionable isotope, so it can go through this fission, such as uranium-235. It has to be present in a quantity that will provide that chain reaction. In the US, about 99% of that uranium is this type of uranium, and only 0.7% is this. That's why people are always like, well, we could make a nuclear bomb out of a power plant. You can't, because the material in there, there's not enough of it to make a bomb out of. So people don't need to worry about, well, somebody could come in and take over our country and make a bomb out of this. It's not pure enough to make that happen. So in order for it to happen, in order for them to be able to use this material as a bomb, they would have to do something called enrichment. And that's what they were worried about, like over in Iraq or Iran several years ago. They would go in and inspect those plants over there to make sure that they weren't trying to enrich that. There has been talk that the Russians were trying to do some of this using the power plant over there, Chernobyl. I don't know. That could be just some urban myth too. I wouldn't swear to that one, but you know how there's conspiracy theories everywhere about all kinds of stuff. All right. Nuclear moderators then is a substance that's going to slow those neutrons down. They used to use graphite, like is in your pencils, as a moderator, but now they usually use just water. Some reactors in other countries then also use these items. All right. Nuclear moderator is a substance that slows the neutrons to a speed that is low enough to cause fission. And like I said, they typically they use water at this point. As far as coolants are concerned, we have here in the US an overlapping cooling system versus just a primary one. And in the US, we tend to use water in that as well. I don't remember. Yeah. So what they do is they have this core in here where they have it heating this water in the kind of the orange color here. And then they have an overlapping cooling system out here so that the water that's being moved around in here never comes outside of that reactor, this water. And then this is the water that's cooling it. And so those water paths never cross each other. So you don't get this cross contamination. Now in Russia, they don't do that. All right, the control rods then control fission by adjusting the number of neutrons so that they'll use something like boron here. That boron then will pick up one of these neutrons and breaks these apart into two different particles and doesn't produce any new neutrons. So it'll take one in, but it doesn't give any off. The control rod assemblies then are inserted into the fuel element. They're going to absorb those slow neutrons. And the fewer neutrons are absorbed, the more it'll increase. And in emergency situations, they can actually drop those control rods in between the fuel rods and it'll soak up every neutron. Good. So they also have a shielding situation here where they will shield the nuclear reactor. It's going to, they can even shut it down. The operating reactor then is thermally very hot, and under the high pressures, the circulation of water, they'll cool it. And it has to be able to withstand these high temperatures and pressures to protect the operating personnel and like people out in the city and everything. Okay, so that's essentially fission. Fusion then is where we take a bigger particle and we're going to break it up, or we're going to take two small particles, and create a bigger particle. And this is what the sun uses to create its energy and your stars. So you're taking this light nuclei and you're kind of like jamming it together. They're fusing it together into a bigger particle. And like I said, this is how your stars work. They've tried to do this fusion here on Earth, and they've accomplished it in like bombs. And I think that they might have done it like in a couple reactors, but it takes so much more energy to get it started than you get out of it that it's not, it doesn't net, you don't gain anything. You lose energy in the process. So they haven't been able to figure out what they call cold fusion, fusion at room temperature, to be able to get this to work and give a sustainable source of electricity. If they can, then all of our energy woes are solved because we have enough hydrogen that we could create this energy forever and not have to worry anything about trying to create electricity. So that, my dears, is chapter 4.